Hey, Joe, we got some folks coming over a little bit later to do some work in the boiler room. Will you bring me all the diagrams for Load Center 308, Unit 3?
Okay.
And bring me a schematic of one of the pumps. Make sure it's the latest revision. A few things I want to go over with you.
Okay.
The two men that you just saw know how to use an electrical diagram. An electrical diagram is a piece of paper with lines, symbols, and letter and number combinations that accurately represent electrical circuits. In this lesson, we'll show you how to use electrical diagrams to better understand and find your way around electrical circuits. There are many different types of electrical diagrams. They're drawn differently, and they provide different information. In this lesson, we'll cover 4 types of diagrams that you may use in your day-to-day work. Those diagrams are the block diagram, the single line diagram, like this, the schematic diagram, and the wiring diagram. We'll discuss how you can use these different diagrams to make new installations, locate troubles, and make modifications to existing circuits. We'll show you what information is contained in these diagrams and how you can get this information and apply it to some actual jobs. And you'll see some of the symbols used in electrical diagrams. Some of these symbols may be drawn differently, but represent the same component. We'll show you only a few of the symbols. You'll see many more in your day-to-day work. Your text will have many more symbols than what we'll show you here. Now, in our opinion, there are 3 things that good electricians must be able to do and do well. They must be able to use electrical test equipment, read and use manufacturer's equipment manuals, and read and interpret electrical diagrams. How well you can do these things will determine, to a great extent, just how effective you will be in troubleshooting and maintaining electrical equipment. Regardless of how much or what you study, this is one of the most important lessons that you'll have, so pay close attention and learn every detail you can concerning electrical diagrams. In your plant, electrical diagrams may be given other names. For instance, you may hear them called prints. They're also commonly called blueprints. However, since those terms, print or blueprint, often refer to drawings other than electrical diagrams, we'll use the term diagram in this lesson to identify electrical drawings. Before we start to look at some actual diagrams, here's another bit of general information that you should know. A set of standard numbers have been set up to identify the general function of many electrical devices. To be exact, there are 100 of these numbers, and they are listed as the American Standard Device Function numbers. In your text, you'll find a complete list of all 100 numbers and their definitions. Now, before we go on to learning how to read electrical diagrams, there is another table we want to show you, the Standard Diagram Abbreviations table. We're going to mention just a couple, but the entire list is contained in your textbook. One example of a standard diagram abbreviation is CS. That is the abbreviation for a control switch. Another example is HC. That is the standard abbreviation for a holding coil. Take a few minutes to look over the symbols and numbers in the appendices of your text. You'll be seeing and hearing about them throughout the lesson. If you have any questions, ask your instructor. In the previous segment of this lesson, we discussed some number symbols and standard abbreviations used in electrical diagrams. We also mentioned some different diagrams we're going to cover. In this segment, we're going to discuss the block diagram. But before we go over the actual diagram, let's take a few minutes to look at some of the other information on the diagram and see what it's for. First, let's look at the title block. Title blocks are usually located on the bottom right-hand side of a diagram. The title block contains a good deal of useful information about the diagram. First, it tells you the name of the diagram. This one is a block diagram for a 480-volt load center. The title block also tells you what the unit is for. Now, this is fairly important because if you're going to work on unit number 3, you really should have the diagram for unit number 3. That seems kind of obvious, but seriously, be sure you check to see if you have the right diagram. Another portion of the title block that can be very helpful is the revision block. This block contains the general description of the revision number, and the date of the revision. You'll always want to use the diagram with the latest revision. Revisions are usually made when something is added or removed from the system. If you're not using the diagram with the latest revision, you may be tracing a circuit that no longer exists in the plant. If your files have several diagrams for the same unit, always use the one with the latest revision listed. Okay, here's another important feature of this diagram, the notes. This one only has 2 notes, but electrical diagrams can have many. The notes usually give detailed information about specific portions of the diagram, or they may list other references you may need to go along with the diagram. The notes may also define in detail the latest revision of the diagram, so you should look them over when you're using the diagrams. Another extremely useful part of the diagram is the legend. The legend identifies diagram symbols and any unusual designations on the diagram. The legend is a part of this diagram sheet, but in many cases it may be on a separate sheet. All right, you've seen some of the important general features on most diagrams. Now we're going to move on and talk about block diagrams. This is a very simple block diagram, but then block diagrams usually are simple. They don't have much detail, and they don't give you much in the way of information. What they do give you is a basic overview of the system and how components are connected in relation to each other. Blocks are used to represent the major components in an electrical system. Notice that the name of the components illustrated by the blocks is spelled out. Block diagrams do not accurately show the physical location of the components. However, in some block diagrams, the component's physical location may be spelled out either inside the block itself or near it. The single line between these blocks indicate that they're electrically connected to one another. This line may represent only one cable, or it may represent several. Block diagrams won't usually tell you if the line symbolizes one or several cables. Now, let's take a look and see how a block diagram can be useful to you. In this diagram, the first thing that we see is exactly what components are located in this system and what electrical order they're in. In this system, the circuit goes from a transformer to a distribution board, which is labeled on the block diagram as being a 480-volt load center, number 308. From the distribution board, or load center, we have several lines going out to various parts of the plant. So the diagram shows what components are in the system. and where they're electrically located in relation to each other. If you were new in the plant, or you were not familiar with the system, the block diagram can show all of the components in the system, from the transformer to the end of the system. By using this type of diagram, you can learn what components in a system could cause another part of the system to fail. For example, let's say that the lake water pump doesn't run. You could tell just by looking at the block diagram that the lake water pump and its associated power equipment get their power supply from a 480-volt bus, number 308. So, as you can see, the block diagram gives the maintenance electrician a place to start looking for a possible problem. In this case, the 480-volt load center, number 308, is a place for the electrician to start looking for a problem. Okay, so far we've discussed the information contained in the title blocks and how you can use the information. We've also looked over a simple block diagram. Before we go on, look over your text and answer the questions you'll find in there. If you have any additional questions, ask your instructor. Single line diagrams. A single line diagram illustrates all circuits as one single line. It's laid out in the same basic way as the block diagram that we talked about in the last segment, but it uses standard symbols, electrical symbols, instead of blocks to represent the major components in a circuit. It also contains more detailed information, and it may identify the general plant location of major components. Let's take a look at a typical single-line diagram, discuss the information on it, and explain how it can be used. This is a diagram of a 480-volt load center. This one is relatively simple, but it is fairly typical of most single-line diagrams. It uses fairly standard symbols, and it uses the American Standard Device Function numbers. We're going to go through the diagram and show you how all the information on the diagram can be used to give a picture of a typical electrical system layout. This line indicates the power path. Now, this single line may represent one single wire, or it could represent several. Regardless of how many wires there are in a circuit, a single line diagram will indicate them all by one single line. When we're following single line diagrams, we're not specifically following voltage or current. We're really following the power path through the system. These other single lines and symbols are indicating and control circuits that can control and protect the power circuit. We'll talk more about them later. Now, when we look at this line, we see that at the very end of the line, it has an arrow that is pointed at some information. The information is this system goes to a 4,160-volt switchgear bus, number 32. It also tells us to look at the diagram number GES NUS 003. Now, if we wanted to go over that switchgear unit, we would have to get that diagram. But we're not. What we want to discuss is on the diagram. So let's follow the power path through the diagram and see what we can learn. Following this single line down, the next bit of information is a small circle and the number 31C500 MCM. That tells us the number of wires represented by the single line, what kind they are, and the wire size. The 3 means that there are 3 wires in the line. The 1/C means that they're single conductors, and the 500 MCM is the size of each conductor. So that means that this line is made up of 3 single conductors, and they're each 500,000 circular mils in size. Now, just below is the standard symbol for a power transformer. This symbol is usually accompanied by other symbols or numbers to identify the transformer and the way it's connected. The information to the left of the power transformer symbol tells us what transformer it is. This one is designated number 308. It also tells us that it's a 4,160 to 480 volt, three-phase, 60 hertz step-down transformer. The first number reading from left to right is usually the primary voltage for a transformer. The primary of a transformer is always the side that is connected to the power supply. These two symbols mean that the primary of this transformer is connected delta, and the secondary is connected Y. They also indicate that the secondary of the transformer is also grounded, and that it's connected to a ground through a resistor. A ground connected to a resistor like this is called an impedance ground. As you probably know, impedance in AC circuits is the total opposition to current flow. The resistor is installed in the ground circuit to limit the amount of current that can flow in the circuit. Now, let's look at the information on the other side of the power transformer symbol. Here we have a line coming off this ground resistor to a block labeled TS. This is not a standard symbol, but there is a section of the diagram that will explain non-standard symbols. Okay, let's look at the legend. It tells us that the symbol is a test switch. We'll explain in just a few minutes what it tests. Attached to the TS block is a circle with a standard device function number in it. The number is 59N. Number 59 is one of the American standard device function numbers. Number 59 is the standard device number for an overvoltage relay. This is a device that functions on a given value of overvoltage. The letter N means that it's hooked to a neutral. This relay is designed to operate its contacts if the voltage across this resistor exceeds a predetermined value. The diagram we've just been looking at does not explain how the relay works or at what values. That information would be contained in a schematic diagram drawn for the particular relay. We'll cover schematic diagrams in detail later on. Now, the test switch that we mentioned earlier would be used to test this overvoltage relay. How it does this is also contained in a schematic diagram. The next symbol we see is the standard symbol for a current transformer. This symbol is usually accompanied by numbers to identify its primary to secondary current ratio. In this case, the 3000/5 to the right of the symbol is the primary to secondary current ratio. In other words, if we have 3,000 amps of primary current, we'll have 5 amps of secondary current. Okay, attached to the current transformer, we have a block with the letters TS. This is another test switch. Attached to the test switch is another standard device function number, number 51. 51 is the standard function number for an AC time overcurrent relay. An AC time overcurrent relay is a timed relay device that's designed to operate on a specific amount of overcurrent in the circuit. It's also designed to give a specific time delay before it operates to allow some overcurrent surges, but not a prolonged overcurrent that could damage the circuit. The test switch allows the operator to test the overcurrent relay by applying an overcurrent to the relay. Here again, the how and why is contained in a schematic diagram. The next thing we're going to look at is the block labeled with the letters AS. A quick look at the diagram legend tells us that the symbol is for an ammeter switch. This type of switch is usually a selector switch. A selector switch will usually have several positions that allow the operator to choose which phase of the circuit he wants to check. The next symbol is a circle with an A in it. This is the symbol for an ammeter. By using this ammeter switch, the operator can use the installed ammeter to check current flow in any phase of the circuit. Okay, the next symbol we're going to discuss is the standard symbol for a circuit breaker. Here it is. The information on the diagram tells us that it's a 3,000 amp breaker, And the standard device function number 52 tells us that it's an AC circuit breaker. All right, now we're down to the bus. A bus is an assembly of electrical conductors designed to be used to distribute power to other circuits. A bus assembly is frequently called bus work or bus bars. The 308 is a local number assigned to identify this bus. The 3000 amp notation designates the bus as capable of carrying 3000 amps. Now, coming off of the bus, we have 6 lines all going to standard symbols for circuit breakers. Each of these circuit breakers carry the standard device function number of 52, so we know that they're AC circuit breakers. However, there is some new information listed on these breakers. Notice that there are 2 sets of numbers on each breaker. The first number, 600 in this case, indicates the frame size of the circuit breaker. As you probably know, many circuit breakers are manufactured in standard frame sizes, and they're designated by the maximum amperage that they can carry safely. Okay, the second number is the size of the trip element used in each breaker. The trip element determines the maximum current that the breaker can carry indefinitely. In other words, the trip element determines the amount of current the breaker can carry without tripping. These lines leaving the breaker indicate where the circuits go. We can see that 2 of them are spares. The other 4 go to various parts of the plant. This diagram also indicates the size of the wiring leaving these breakers. If we look closely at the 3rd, 4th, and 5th breaker, we'll see new information concerning the wire. This 2 means that there are 2 sets of 3 single conductors of 500 MCM wire in each of these circuits. Okay, we've got one more section of the diagram to look at. Here we have the standard symbol for a fuse connected in series with the symbol for a 480 volt to 120 volt step-down transformer. These 2 symbols indicate that both the primary and the secondary of this transformer are connected open delta, and the secondary of the transformer is grounded. This symbol here on the secondary represents a ground. Okay, the open delta transformer shown on the diagram is a 2-winding transformer connected in a delta arrangement so that a 3-phase voltage can be produced using only 2 windings. The next symbol is another test switch. We'll say more about this test switch a little bit later. The next symbol is the standard device function number 27. This is a standard function number for an undervoltage relay. An undervoltage relay is a device that functions on a given value of undervoltage, or in other words, when the voltage falls below a certain value. The how and why of the function of the relay would be explained in a more detailed schematic diagram. Now, the test switch we mentioned a little earlier is used to test the function of this relay by applying an undervoltage to it. Here again, the detail of the exact operation would be contained in a schematic diagram. To the left of the undervoltage relay is the standard symbol for a voltmeter switch. Right above the voltmeter switch, we have a symbol labeled V. The legend identifies this as a voltmeter.
The voltmeter switch is also a selector switch and is designed to select 2 phases the operator would like the voltmeter to read. In other words, he can test the voltage between phases 1 and 2, 2 and 3, or 3 and 1.
The end of this line indicates that this bus is connected to another bus designated in the plant as 480 volts, bus 307. Well, we've covered a lot of information in this segment, but once you've mastered the art of reading single-line diagrams, you'll find them to be very valuable. For now, take the time to go over the material in your text. If you have any questions, take them up with your instructor. So far in this lesson, we've looked at and talked about electrical diagrams. That'll give you a pictorial overview of a system as a whole. Now, we're going to go over some types of electrical diagrams that will give you a detailed view of specific sections within a system. The first type of diagram we're going to look at and discuss is the schematic diagram. The schematic diagram, which is often called just a schematic, is a simplified drawing showing all of the components in a unit and their electrical connection to each other. This type of diagram is designed so that all the components are in the proper position electrically, but they're not necessarily shown in the proper physical location. Okay, let's take a close look at a typical schematic diagram. As you can see, this schematic uses the standard electrical diagram symbols and numbers we talked about earlier. This particular diagram is a simple three-phase AC motor controller. This is a pretty typical, simple schematic diagram. As we stated earlier, schematics show all the components in a unit. They're usually read from left to right and from top to bottom. The position of the contacts and switches are shown in their de-energized or relaxed state. As in all motor controller diagrams, this one can be divided into two circuits, a control circuit and a motor circuit. This section is the control circuit. The primary function of the control circuit is to control the action of the controller. In other words, the control circuit controls the controller. The other section on the schematic is the motor circuit. Its function is to control the action of the motor. It connects the motor to the power supply. Understanding the circuits and their functions can aid you greatly if you have to troubleshoot the unit. Now, if the controller fails to operate, or in other words, if the contactors and relays do not operate, then the trouble is usually somewhere in the control circuit. On the other hand, if the controller operates normally, but the motor fails to operate, then the trouble is in the motor circuit. Now, let's go through the diagram and see how the schematic can tell us how the controller and motor in the diagram are supposed to operate. Let's look at the components in the motor circuit first. These three lines represent the power supply. The diagram tells us that this power supply is 480 volts, 3 phases, and 60 hertz. These three lines represent the power supply to the controller. Following these lines down from top to bottom, the next symbol we see is the standard symbol for a circuit breaker. You're probably aware that there are different types of circuit breakers. This symbol represents a 3-pole circuit breaker. That means that it can open or close 3 electrical lines at the same time. Now, on the diagram, there was another indicator as to what type of circuit breaker the symbol represented. The device function number, 52, is positioned next to the symbol. It's the standard device function number, 52, and the number 52 is the number for an AC circuit breaker. Now, following the 3 lines down, we have the standard symbol for a transformer. The diagram tells us it's a 480 volt to 120 volt step-down transformer. The next thing in this circuit is the symbol for 3 normally open contacts. In electrical diagrams, normally open or normally closed is the condition of contacts when the device which operates them is de-energized or in its relaxed position. The device function number assigned to the contacts is 42. We'll cover function number 42 in more detail in just a moment. The next symbols we have are the symbols for the overload heaters. An overload heater symbol represents a protective device, and you'll find this symbol in almost all motor control diagrams. This symbol is further identified by the letters OL for overload. The overload heaters are also assigned the device function number 42. Device function number 42 is the number used for a running circuit breaker. It can also be used with other fault protective devices that are connected in series with devices that frequently open and close a circuit. All right, the last symbol is the motor. Okay, that's the motor circuit. Now, let's look at the other part of the schematic, the control circuit. Let's identify the components first, starting here on the left side of the circuit at the transformer. Now, as we discussed earlier, this transformer is a 480 to 120 volt step-down transformer. That tells us that the control circuit is going to be 120 volts. This is done because it's more economical to use components rated at 120 volts than to use components rated at a higher voltage. The next symbol is for fuses. These fuses are installed to protect the control circuit from short circuits. The fuses are designed to blow and open the control circuit to stop the high current that is usually associated with short circuits. The next component is a set of normally closed contacts. They're also assigned the device function number of 42 and the letters OL. These are part of the protective devices we talked about earlier in the motor circuit. They're the overload contacts. Now, let's move over to the next circuit and look at the components in it. Looking up here at the top first, we see that the first thing we have is a symbol for a junction and the number 1. This number is extremely important when you have to troubleshoot a controller. It will help you to locate the junction in the actual unit. Most controllers will have the junction plainly marked and designated by a number or a letter-number combination. In this diagram, the number 1 not only identifies the junction, but it also identifies all the wires connected to it. In this case, not only is the wire going to these contacts designated as number 1, but so are these. This one is going to the fuse. It's designated as 1. So are the ones that go to the lights. So, any wiring coming to or leaving this junction point is labeled as a 1. The information we just told you is extremely important if you want to test a component that is connected to a junction. Later on, you'll see how these junction numbers are valuable to you. The next components we see are 2 normally open contacts and 2 more junction numbers. These 2 junctions, labeled 1C and 2C, serve the same purpose as the one we just talked about. Now, let's identify these 2 normally open contacts. They're also given the device function number 42, along with the letters CS. CS is the standard abbreviation for a control switch. However, at this point, we need to know how these contacts operate. We talked earlier about many diagrams having a legend. The diagram we've been talking about has a legend to describe the function of the control switch. On some diagrams, the description of a control switch is called a switch development chart. This block is a simple drawing of the control switch as it would look to you. These blocks contain the information you would need to determine the position of the contacts in the run position or the off position. This indicates that in the run position, both contacts will be closed. These 2 X's indicate closed. In the off position, both contacts are open. The information below the switch legend tells us that they're maintained contacts. In other words, when the switch is put in the run position, the contacts close and stay closed until the switch is put in the off position. Then they'll open and stay open. We'll get back to the control switch in a few minutes, but right now, let's look at the other components we have in the circuit. This is the standard symbol for a holding coil. It's been given the function number of 42, along with the letters HC. As we've discussed earlier, function number 42 has been assigned because the device opens and closes the circuit frequently, and it's connected in series with a circuit breaker or other protective devices. The letters HC are the standard diagram abbreviation for a holding coil. The coil shown on the diagram is the operating coil for a contactor, and it holds the contactor's armature closed when the coil is energized. Now, let's look at the remainder of the schematic. Here we have 2 symbols for indicating lights. One is designated by the letter R, meaning it's red, and the other by the letter G, meaning that it's green. We have two more symbols we need to discuss. One is for normally open contacts, and the other is for normally closed contacts. They're both assigned the function number 42, which means they're part of the devices that can open or close a circuit frequently. The small letters mean that they perform auxiliary functions. We'll see more of them and talk more about the schematic in the next segment. Okay, we've defined what a schematic is, and we've discussed some of the symbols used in the schematic diagrams. Now, why don't you look over your text and answer the questions you'll find in it. If you have any additional questions, ask your instructor. In the last segment, we defined what a schematic was and some of the symbols used with it. Now, in this segment, we're going to trace out a motor controller schematic, see what it does, and see what it can cause the motor to do. We're going to start in the control circuit, because if we can make it work, then the motor should work. Since this is an AC circuit, and since AC current is constantly changing in value and periodically changing in direction, we have to make an assumption as to which way current is flowing through this circuit. To do that, we can assume what is called an instantaneous value. What this means is that we establish a polarity at some point in that circuit and assume that this polarity doesn't change. Let's do that and see how it works. We're going to start here at this point, and to have a complete path for the current flow, we must be able to return to the other side of the transformer. Now, this is a vital point to keep in mind. In order for electrical circuits to work, there must be a complete path for current flow from one side of a power supply through the circuits and back to the other side of the power supply. Okay, let's start. Leaving the point on this side of the transformer, we go up this line through this fuse that protects the control circuit from short circuits to this first junction. From here, let's go down to the control switch. Now, both sets of contacts are open and current flow stops. There is no complete path through the control switch to this side of the transformer, so this part of the control circuit cannot be energized. Well, let's look at the rest of it. Here we have another line that goes through a red indicating light to another set of normally open contacts. There is no complete path through the red light to the transformer, so the red light is off. Now let's look at the last part of the control circuit. Here we have another line that goes through a green indicating light to a set of normally closed contacts. Since these contacts are closed, there is a path for current flow through the contacts. We also have a path for current flow through these normally closed overload contacts and this fuse to this side of the transformer. So we do have a complete path for current from one side of the transformer back to the other side through the green indicating light. So the green indicating light is on. The condition we've just described is the normal condition for the controller with the control switch in the off position. What you just saw was one of the uses for a schematic diagram. You can trace out a circuit and determine what the system should do in certain conditions. In this case, you saw the off condition. Now, before we go through the diagram with the control switch on, look over the material in your text. If you have any questions concerning any of the material covered up to this point, get them cleared up with your instructor before we go on. So far, everything we've discussed on the schematic has been with the control switch in the off position. Now, we're going to turn the control switch on and go through the diagram one more time. According to the diagram's legend, when the control switch is in the run position, both sets of contacts are closed. Okay, now we're going to assume the same instantaneous polarity as we used before. Starting from the transformer, current flow will go through the fuse up to this point in the circuit. Now, the current can go down this line through the now closed contacts in the control switch because we have the control switch in the run position, through the holding coil back to the other side of the transformer. The path for current flow is complete. The holding coil is energized and the contactor operates. All the contacts associated with this contactor change from their normal position to their energized position. This change takes place almost immediately, unless the schematic tells you that the changes are speeded up or delayed for some reason. In the example we've just described, the changes will take place immediately. As a general rule, when a contactor's operating coil is energized, all the contacts operated by it will change positions. That is, all normally open contacts will close, and all normally closed contacts will open. Looking at the control circuit, we can see that this set of contacts in the series with the red indicating light has now changed from normally open to closed. We now have a complete path for the current flow through the red indicating light, so the red indicating light comes on. This set of contacts in series with the green light is now open. The set of contacts opens the path for current through the green indicating light. Now, if we look at the control circuit as a whole, we see that the holding coil is energized. The red light is on, and the green light is off. In the motor circuit, we have 3 sets of normally open contacts that are now closed. So now we have a path for current flow through the 3 closed contacts, and the motor will run. You might have noticed that we did not assume an instantaneous polarity in the motor circuit. The reason we didn't is because we're not really interested in a path for current flow through the motor. We were only concerned that all 3 lines from the power supply to the motor were complete circuits so that power could be applied to the motor. Now, let's take a look at the whole diagram and see what we have. The holding coil is energized. The red indicating light is on, and the motor is running. That is how this motor control unit is supposed to work, and we learned all this from a simple diagram. What you just saw was one of the uses of a schematic diagram. It gives a detailed electrical description of how specific sections or units of an electrical system are supposed to work. So, by using a schematic to determine how a unit is supposed to work, it can help you to learn where a fault is if the unit does not work the way it's supposed to. Next to your own knowledge and experience, the schematic is probably the most valuable tool that you'll have as you perform your day-to-day work. However, as with most good tools, the schematic does have some limitations. It illustrates all the components in a specific unit in their correct electrical position in a circuit, but it does not indicate where the components are physically in the unit, nor their physical relationship to each other. To locate the components physically in a unit, you have to use a wiring diagram. This is a wiring diagram of the same unit that we just talked about. Looks a bit different, doesn't it? Well, it's drawn to serve a different function from the schematic. This diagram shows the physical location of the components in a unit. It will also show the physical relationship of individual parts of a major component to each other. The best way we've found to use a wiring diagram is to locate one of the major components in the unit and then identify all the other components in relation to it. Let's use the holding coil as the major component. Now, let's find it in the controller. Okay. Now, all of the other components can be located using this holding coil as a reference. The other components will be physically located above the holding coil, below it, or to the right or left of it. They may also be located behind it, and in some cases, they could be in front of it. Now, wiring diagrams are not usually drawn to scale, so the location of the components on the diagram will not be exactly in the proper position. But they will be in the general area, close enough for you to locate them. As you saw, the wiring diagram is a jumble of lines representing the wires. It's very difficult to read and use to troubleshoot with. So don't use it for that. When using diagrams to troubleshoot, use a schematic to do the troubleshooting and use the wiring diagram to locate the components that are to be tested. Now, here's a little trick that can be used to locate specific components in a unit, and that's by using the schematic and the wiring diagram together. Let's look at the schematic diagram first. We'll pick up a point here and see if we can find it in the controller with the aid of the wiring diagram. Let's see if we can find this particular set of contacts. Now, trying to locate a single set of contacts, especially when there is more than one set alike, could be very difficult. But by using the schematic and wiring diagrams together, we'll show you how it can be done relatively easily. Here's the set of contacts. The easiest way to find a single set of contacts is to locate a major component that they're attached to. Since they're auxiliary contacts operated by the holding coil 42HC, we can assume that they'll be part of the contactor. Here on the wiring diagram, we easily found the holding coil. To the left of the holding coil, we see two sets of contacts. One set is normally open, and the other is normally closed. Now, the set we want is the normally closed set. Let's look at the schematic again and try to find some references to positively identify this set of contacts. The best way is to see what they are connected to. If we look at this side of the normally closed contacts, we see a junction point labeled 3G. On the other side of the normally closed contacts, we see that this line goes to the other set of normally open contacts, to the holding coil, and to the normally closed overload contacts. So, what we need to find is a wire labeled 3G. Let's look at the wiring diagram again. This is connected to a set of contacts. We need to find the wire that is connected from the other side of the closed contacts to the set of normally open contacts, the holding coil, or a set of overload contacts. Now, let's look in the controller and see if we can find them. This controller has been electrically isolated and tagged out in accordance with the plant's procedures. However, before the electrician puts his hand in here, he'll check for power with his voltage tester to be sure it's de-energized. When the electrician has determined that the power is off, then the unit can be touched. Now, according to the wiring diagram, this is the set of contacts he's looking for. Well, this wire connected here is marked 3G. That's one of the wires we're looking for. Now, he'll check the wire on the other side of the contacts. This wire is actually a short jumper wire connected to the set of normally open contacts. Another wire is also connected to this terminal. Tracing that wire, we find it's connected to the holding coil. This other wire is connected to the overload contacts. So now we can be sure that this is the set of contacts that we were looking for. You just saw a fairly simple way to locate specific components in a unit and be reasonably sure that you've located the correct component. Schematics and wiring diagrams can be used together to make even very complex electrical systems fairly easy to troubleshoot. So, you use the schematic diagram to locate a possible faulted component, establish some other references to positively identify the component. Then, locate it on the wiring diagram to find its general physical location. After that, locate the component in the actual unit. Check the component with the references you've established so that you know you've found the right component. Then, do the work on the component you were assigned to do. The schematic and the wiring diagram can be two of the most valuable tools you'll have. They can, when properly used, tell you almost anything you need to know about any specific unit. The information we've given you here can give you a start at being proficient in using schematic and wiring diagrams. We've also mentioned some of the tricks experienced electricians use that may help you to use the diagrams more effectively. How good you become at using electrical diagrams is really up to you. It takes time and practice to become good at anything, and reading electrical diagrams is no different. Practice your skill of reading electrical diagrams. Once you learn how to use them, they can be very helpful.